ready for lecture 7. And the topics then would be the first time we're seeing differential equations. Let me copy that equation up here. And I hope you might guess that it's completely analogous to our matrix equation. So this is going to be A transpose minus d by dx. This, you remember we had the diagonal matrix C. Well, now we've got with a discrete set of spring constants. Now we have an elastic constant all along the bar. So I'm thinking instead of, before we had a line of springs with masses, and now, so this is for A transpose C A U equal F. That was the discrete one. The continuous one will be, if we want to, so you can tell, part of the point here is to get the analogies, because I think that's sort of a part, something that mathematics can contribute, to see the same pattern appearing in different places. And here we have the pattern appearing in the discrete problem and in a continuous problem. So I'm thinking here of an elastic bar, you could say, of length. So we make the length 1, so we'll run from x equals 0 to x equal 1. And then we'll end up with this differential equation. So again, we have this displacements, but now the displacements are a function of x. So this is the displacement when gravity acts, or when we put some weights on the bar. For example, I might put on a weight, tack on a weight right there at a point x equal a. I might tack on a weight w. So that would pull. It's worth really thinking. I mean, these are problems where even if we're not mechanics specialists in mechanics, we can see what that will do to what displacement that might produce. So there'll be a function u of x. There will be a stretching. And what will that be? Well, this is the operator A, and the stretching is du dx, is the derivative. And that's sort of right. I mean, in this case, the stretching was, you remember what the operator A did? The stretching was the E. So this is E, if we keep that same symbol. The E here in the discrete case, what was E? This one dropped by U1, and this point, well, either didn't move or moved by U0. So E was U1 minus U0. It was a difference operator. Now, in the continuous case, we would just expect, and it happens, that the difference operator turns into a derivative. It was a first difference, and it turns into a first derivative. And then comes Hooke's law, the constitutive law, and that's a multiplication by C of x, and produces W of x, the internal force. This is like internal force. So these E, the U up here and the W down there are still the principal unknowns. And then there's going to be an A transpose, and there's going to be an equation minus dw dx equals f. And what will that equation represent? So as before, we have sort of a geometry, if we know the displacements, then we can see how much a little piece is being stretched. That's the derivative. Then we multiply by C to connect to the force that does that stretching. So that's the internal force, W. And then what does that equation indicate? Tell us something about. Sorry. Yeah, we have exactly. The internal balances the external. It's a force balance. Force balance, exactly. Okay. And by the way, I've mentioned delta function there on my general outline. Let me put in that this, where does the, we have to sort of like get, it's worth getting familiar with the delta function. And it's in my picture here, it's going to come up right away. What's the external force in this picture? We may have some weight from the bar. That would contribute an f of x all along, a force right the length of the bar. But what would be the contribution from this point load? This is a point load, and I think it's really worth getting the hang. Well, it's almost a pun, but getting the idea of a point load. And so that point load in math terms here would be W, the weight to get the units right, and then the fact of being a point load, I use this delta function. And it's a delta function that has its spike at A, at that particular point. So delta of x. So can I go with this delta function idea a little bit while we're fresh? So just a discussion about delta functions and step functions. Okay. Because, well, what I want to show is if we can deal with right-hand sides being delta functions, then that's sort of like the basic right-hand side. That's your basic right-hand side is the delta function at different points. If we can deal with those, we can deal with any f of x. Somehow any f of x is somehow an integral of delta functions. So it's the delta function that's the most basic. Now, the basic delta function is delta of x. And what is it? I don't know. It's often described as an impulse. Here we're using the words point load, spike, I sometimes use. If I try to graph it, I can't do justice to it. But let me try. If I graph the function, it's 0 until the origin, until I hit that particular point. And then it's something amazing at that point, and 0 after that. So it's like everything is happening at that point. And of course, everybody sees delta of x minus a. What's the effect of translating, shifting the variable? What would so now if I tried to graph delta of x minus a, what would change in the graph? The spike would be at A, right? Because it's wherever this thing is 0, and it's 0 at A. So that would be delta of x minus A, no problem. Okay. Often, so if we understand delta of x, we no difficulty with the shifting of it. Okay, so that's a delta function. And, but now I didn't say the main point, right? What's the main point about that delta function? It's so powerful at that one point that its integral is 1. It has it's an impulse. It happens in an instant, so no true function can do it. It happens in an instant, but what it does in that instant is the integral jumps to 1, and the integral is the step function. Let me put this back to 0. Oh, well, I can leave it at A. So what's the graph of its integral? This is the integral of the delta function. Is that right? Yes, the integral of the delta function. Okay. So the delta function it's worse than a step function. Integration always smooths things. Differentiation always makes them noisier. So here we're going in the smooth direction. So what happens then if I integrate this function? So I integrate delta of x minus a. Say integral of delta of x minus a dx from, let's say, I could start at minus infinity because nothing's going to happen back here. And let me go to an arbitrary point, say, capital X. So can I graph that now? So now it's a function of capital X. The choice of variable isn't too crucial. Okay, what's the integral then of the delta function? You know it, but just to see it. So the integral as I'm coming along here is 0. So I'm coming along, and then I hit, oh, good, I hit the crack in the blackboard. That's A. And after that, the integral jumps up to 1. Right. And then doesn't change after that. So it jumps up to 1. Okay. So the integral of this function, not a true function. I guess it's associated first of all with the name of Heaviside, Heaviside, Oliver Heaviside, who was among the first to do what we're really going to do, just deal with it. It was sort of legitimized as, and given a new name, a distribution, by Schwartz, Laurent Schwartz. So the theory of distributions is the theory of dealing with functions like the delta function, and worse than that, the derivative of the delta function. So if I go in the other direction to take derivatives, I'm really getting stranger and stranger functions. For the moment, let's go that way. Okay. So I would like to be able to put that on the right-hand side. So here will be the kind of examples which we can solve in detail. I'll take C of x to be identically 1 in these examples. So it's like C is the identity matrix, and I'm back to my nicest case, A transpose A. I mean, A transpose A has sort of really got the guts of the problem in it, and C of x, or the matrix C, just is a necessary a useful generalization, but the heart of the problem is in A transpose A. Okay, so examples with C of x is 1, then my equation becomes simpler. It's just minus the second derivative of u equals, and now let me take a delta function at A. I'll even let w be 1 just because no use to make it more complicated than necessary. So that's my differential equation. And now, so 2 or 3 things coming to my mind here. We've got to have boundary conditions. We would expect 2 boundary conditions because we have a second order equation. And we'd expect a boundary condition at one end and a boundary condition at the other end. This is a boundary value problem. That's very different from an initial value problem. Initial value means we give everything at time 0 and go. In that problem, the eigenvalues appeared. We saw some of those last time, and we'll see more for partial differential equations. Heat equation, wave equation. Things happen in time. Here, there's no time. Steady state. It's equilibrium. It's a boundary value problem. In partial differential equations, we would refer to an elliptic, a partial differential equation of elliptic type. And my second lecture today will be about the Laplace equation, which is the absolute sort of prototype of boundary value problems for PDEs. Here we have boundary value problems for ODEs. So I'm expecting a boundary condition at the top and expecting a boundary condition at the bottom at x equals 0 and at x equal 1. Why don't we put in the boundary conditions that are appropriate for that physical model? So what's the boundary condition at the top? U equals 0. Right. U at this point is 0. So the boundary condition that I'm seeing here is U of 0 equals 0. Let me copy that over here. U of 0 equals 0. Okay. And now what boundary condition? That's fine. And what boundary condition am I going to see at the bottom end in this picture? W is 0, right. W is 0. The boundary conditions are on U or on W. And so it's W at the point 1 is 0. So that would be W of 1 is 0. And of course I can write in what W of 1 is. It's C du dx at 1 is 0. Is 0. Okay. Good. We could solve that equation. It's kind of fun, actually, to solve that equation. And we can so let's do it. And we can make the analogies with the discrete problem. With the discrete problem where we had maybe like 2 masses and 2 springs, and that mass was hanging free just the way that's hanging free. Why was the answer W equals 0 here? I always, if you tell me the right answer, I write it down right away, and I don't always remember to say more. Because there's nothing, right, equilibrium at that point. There's nobody here, right? There's no force here, so, and the force is W. And the force is, yeah. So the force has to be, there's nothing pulling on that bottom of the bar. The bottom of the bar is hanging free. So we're speaking here about fixed, free boundary conditions. Of course, you know that I'm going to, when I've said examples, another one is going to be what? Another one of interest is going to be or U of 0 equals 0 and U of 1 equals 0. Fixed. Fixed at both ends. That would be a different example to be solved in a different way, actually. So those are the two sort of model examples. I'm sort of inclined to jump into those to say how would we would actually find those solutions. Okay. Before I jump in, I'm always open to questions, and I have a question for myself, and that is, I wrote down this framework and this differential equation. Without much discussion, right? And in particular, I didn't discuss this little surprising business here that A is now the derivative, so that AU, the derivative of U, is E, the next step. And what's A transpose? That's what I realized. Wow, where did that come from? And what is A transpose in this analogy? And it's only an analogy right now. Is minus the derivative. So what's up? So A transpose is minus the derivative. These, I would use maybe the word operator for something like the derivative, where this was where A was here was a difference matrix. It multiplied U and produced E. It acted on U. Matrices act. That's really the point. Matrices act. Operators act. You give them an input U, and they give you back an output E. It's a matrix. A matrix in particular, we use it kind of in two ways. We think of a matrix as kind of maybe just a storage of an array of numbers. It's just like sitting there. That's not so much what we're doing here. I mean, that's convenient to have a bunch of numbers stored in a rectangular array. Here, our A is, and the A over here, is operating. It's acting. It's taking an input and producing an output. And for some reason, the derivative is, the first derivative is somehow anti-symmetric, right? That's what, if this is true, and I haven't, so this, the reason I circled those is to come back to that. But for some reason, the first derivative is, we're seeing that if the first derivative is A, then the transpose is the negative, is minus, is minus A. So, morally speaking, the first derivative is anti-symmetric. Sometimes I would use the word skew-symmetric, just meaning the transpose is minus. Now, I caught myself as I said that. And why did I catch myself? Because in the definition of the operator come the boundary conditions. So, so to speak, in the middle of the interval, I'm totally happy to say that derivative is anti-symmetric and its transpose is minus the derivative. But I have to pay attention also to the boundary conditions. And the boundary conditions, these go with A. The boundary conditions on U are part of the definition of A. A is the derivative, and it acts on functions that satisfy the boundary conditions. Functions U of X that satisfy the boundary conditions on U. A transpose is minus the derivative, and it acts on functions W that satisfy any boundary conditions on W. So maybe I just make the point here. Here I've got two boundary conditions on U and none on W. So, so it's not really quite legitimate for me to say that A is anti-symmetric. It's pretty anti-symmetric, the derivative, except the functions it's acting on are different. And also here, we have a boundary condition at one end on U and a boundary condition at the other end on W. What I really want to emphasize is that boundary conditions are part of the problem and often the hardest part. I really have learned in many years of leaving my office door open and people come in and they always say, I just have a little question. Okay, I know I'm in trouble. And I hope you'll say that too, because I don't mean trouble, I mean it's good. I know it's not going to be a little question and I won't know the answer. But it's very, very often about boundary conditions. You know, their thesis is buzzing along, they've got the differential equation, and oh, if it was just a little bit clearer, what are the boundary conditions? And often, they're doing it numerically. They're replacing this differential equation by finite differences. And then, what do? What's the finite difference? What finite difference? What's the what's the discrete form of the boundary condition? That's like a real issue. Still more to be learned. Not everything is known about that topic. And of course, the point is there's not just one discrete form. If I have a boundary condition like derivative equals 0, well, how do I replace that by finite differences? A lot of possibilities. Every possibility. Do you see that where are these boundary conditions going to show up in our matrices? I'm making you think back to the matrices that we saw from the very first day, in fact. And keep those in mind at the same time as dealing with the new problem. So where did we see boundary conditions showing up? So I don't know if we even used the word. In our matrices. You remember our matrices were, so I'll just follow up that discussion. One of our matrices, our favorite, almost, favorite of some, was that K, and we discovered that that was an A transpose A. And so I want to talk about that again while we're fresh. I'm jumping onto that one. The boundary conditions are somehow part of A and A transpose, and we don't deeply understand A and A transpose until we got to hang on those boundary conditions. Yeah. So this was the operator we called K, right? And what do you see? What do you remember from the springs? What boundary conditions? Which of our two problems that's going to come from? It's going to come from fixed and fixed. Somehow, the -1 that ought to be over here that multiplied u0. You remember this multiplied like a u1 and u2 and a u3, and then there was a u4 that was. These were 0. It was this problem. It was this problem that led to, I'll put it in, K. And now I'll come back in a second to that problem. Do you see that here we have, so what are the analogies that I want to make here? I want to indicate that by dropping this u0, by taking it as 0, we were, in a simple way, applying the boundary condition. And at the bottom end, where we have the same picture, there's a -1, not neglected, thrown away, because it would multiply. You see that when I do that multiplication, that -1 would hit u4, and it's being taken as 0. So in some way, the boundary conditions, so the answer to my question was, the boundary conditions come in the first row and last row of the matrix. When we had the matrices, we had different first rows and sometimes different last rows. So what would, you remember our next example was like that? So what's up there? Again, here is a u equals 0 because we're dropping a -1. What boundary condition is being reflected in that first row of the matrix? U prime is 0. That first row is telling us somehow we've thrown away. You see, what have we thrown away out of the minus? If we really had a -1, 2, -1, then we've said to ourselves, this guy is the same as this guy. So I've really taken the boundary condition that led me to this row was really that u0 was the same as u1. The slope was 0. So this one leads to, I almost drew an arrow to that, but why is this not matching that one perfectly? Because it's the wrong end. Wrong end. So if I wanted it to match perfectly, I should put no slope, the free end down here. So now I've got, at this end, I'm looking at W equals 0, and up at this end, I'm now looking at, as always, at U equals 0. So U equals 0 at top, and W equals 0 at the bottom. Okay. Okay. Oh, let me go a little further with these. Maybe I better take them one at a time, and I guess this was our K that we started with, so let me deal with that one first. I would like to see K as A transpose A. So I'll put this example back up when we're finished with this guy. Okay, I would like to see this K, which is the fixed, right? This is fixed. K is fixed. It's this problem in the discrete case. It's the bottom spring is, there's another spring attached to ground. There's a that one's fixed. Okay, I'm going to stay with these analogies just a little longer to get, because it's all coming now. And then I'm going to solve these equations with the delta functions. So that's my two principal tasks in now. Is first of all to make this analogy, continue with the analogy, and then to say, okay, on with the differential equation, let's solve it. Okay. So what was the A? Do you remember? We actually had an A. This was an A transpose A. What was the A? Let's see. The result is 3 by 3. But there were 4 springs, right? When it was fixed, right? With 3 masses, there were 4 springs. So this is a 3 by 3 came from an A transpose, which was 3 by 4, and an A, which was 4 by 3. And what were they? Let me just remember them. A was 4 by 3. I think there was, let's see, it involved, oh gosh. Can you remember back?
Yeah, I got it.
Okay, you got it. All right. Good to, okay, fine. All right, so ones, it's a first difference. There's a 1 minus this guy, but that's U0 and it's not there. And then there was a U2 minus U1, and a U3 minus U2, and a U4 minus U3. Whoops. That was our matrix.
Yeah. You don't have the last one. Isn't it 2
Ah.
columns and 4 rows?
True. Have I got a 4th row?
You have 4
I do. And why is that wrong? It's wrong. Yeah. And why shouldn't that row be there? You're right. Totally right. Because I'm doing fixed, and U4 is 0. Right. Good. Okay. And now for its transpose. So am I able to transpose that? 1 minus 1, 1 minus 1, 1 minus 1. Oh, you're seeing those. Huh. Actually, we're seeing it all. Do you see that 1 minus 1 as being a finite difference? Of course you do. It's the U2 minus U1 or U3 minus U2. And are you happy if I don't put in all the zeros? Yeah. And do you see somehow morally this minus sign showing up in the transpose? You see it, right? Because in the transpose, it's somehow, yeah, it's reversed. The signs are reversed. It's a difference, and yeah, it may be one. And when we have differences, we might be like forward in the difference, U beyond minus U here, Or we might be doing u here minus u earlier. Those are both okay for differences. Or we might have a center difference, u beyond minus u earlier. That has a lot of value, that centered one. But these are not centered. But the point, everybody's seeing the point that sort of when I transpose that matrix, this was a difference, and this was the difference as a minus sign, because it's well, you see it. Okay, and what? So again, you see why I was only able to say that morally the transpose produced a minus sign, because it did something more. It changed the shape of the matrix. From 4 by 3, we changed to 3 by 4. So we don't, strictly speaking, have here an anti-symmetric matrix. I'm just being picky about this point, that we don't have an anti-symmetric matrix because when we transpose it, we do get a sign reversal, but we also get the other shape. But the point was that when we multiply, everybody's done this multiplication now. We got the 2 and the minus 1s and the 2 and the minus 1s. And we all remember the good properties of K. It's certainly symmetric, of course, because it's A transpose A. And it's positive definite. Why is that now? A transpose A is always positive definite, or at least semi-definite. And what was the point about why is it actually definite? This is non-singular. We're pushed up from 0 because the test was that this A had no null space. There were no combinations of those 3 columns that gave the 0 column. Except, of course, to take 0 of every column. That's always possible. But those 3 columns are independent. The rank is 3. So the rank of this thing is 3. It's non-singular, everything. Positive, definite, all good. Yeah. Okay. And if we wanted to, I could do the same analogy. Let me do the same analogy. Can I do it with the second problem, just while we're doing these things? What will be up with the second problem? So or rather, the first, as I've written it here, the fixed free problem. How could I get fixed and free here? I think I get fixed and free just by, do I get it by just throwing away that 4th spring? Right, the 4th spring was hooking me to the bottom. If I throw that away, so that means I throw away the 4th row. This now becomes 3 by 3. This, is that right? Now I throw away the 4th column here, because I'm transposing. It's 3 by 3. And now what is A transpose A? It now has the new name. But now what's changed in this matrix? This guy has become a 1. Right. When I multiply row 3 by column 3, I'll make it look a little cleaner. There's only a 1 there to multiply the 1. Yeah. And I'm getting the right. Now, actually, there's something else to recognize about. There's another difference to recognize about these 2 problems. And it's in the fact that this one gave us square matrices, where the other problem gave us rectangular matrices. So let me try to write that point down, because it's kind of important. It's kind of satisfying, I think. Okay. So the point I'm just pointing it out, that the fixed free, that led to square matrices, square A, and in this, what it means is, what's good about having a square matrix A? See, normally we have a rectangular. And that's what we have for fixed. Fixed. We have a rectangular matrix A. And in practice, what difference does it make? Well, in this square case, we can solve first for W. The inverse of this matrix, we can invert that one and that one. Of course, it'll go in the opposite order. So in the square case, K inverse is, so K was A transpose A, so K inverse will be A inverse A transpose inverse, and that makes good sense. A transpose has got an inverse. This has an inverse. We can invert separately. Where in the rectangular case, we can't split apart the inverses. And so the conclusion is I must keep it all together and solve for U. Solve KU equal F first for U to give me U. And then later, W. I'm really using every corner of the board here. Do you see what I'm saying? That in this case, it means that I can first W and then U. It's exceptional. This is the exceptional case. Exceptionally easy. It's because the factors allow us to. In other words, what I want to say is that this problem, with these boundary conditions, this is the easier one. We can find W first, and then find U. Whereas this problem, we're going to have to go for U straight off. Okay, I'm ready now to do that, to solve those two example problems. And this is, let me mention where we are in the textbook. We're in section 3.1. And there's a lot in that section. But I'm picking here the heart of it, which is the new framework that for the first time includes derivatives, the boundary conditions, the showing up of a delta function, and the solution of the equations with that delta function. So can we go for that now? Let me solve these two problems. They're different problems. Same equation, but that set of boundary conditions, let me do that one first, and then let me do this one second. Okay. So first I'm tackling the hanging bar with a weight that I've now called 1. It's now a unit weight, so I won't write an amount at a point x equal a. Tell me physically first, before we deal with the differential equation, what's going to happen? If I take a bar, it's a light bar, so its own weight is not significant here. I hang a load, a unit load, at some midway point, partway point. What do you expect? Well, tell me something about the internal forces. Those are the W's. And then I'll ask you about the displacements U. All right, what about internal forces, W? What will be the internal force below the load? Right, 0, right. Because we're assuming this thing is weightless. So there's nothing happening down here, and it's just hanging. Where above the load, the internal force will be that weight W, or which I'm just setting for convenience to be 1. I'm expecting. So now I'm ready. We just solved that differential equation. So let's draw the solution. So I think graphing these. So this is the fixed free. So this is fixed free. just so we keep straight which one we're solving. That means u of 0 is 0, and w of 1 is 0. Okay. And we just found w. And what was it? As a function of x. It changed at x equal a. And beyond x equal a, it was 0. Beyond x equal a, below the load, nothing's happening. It's 0 all the way out to 1. And above the load, for x less than a, the force is 1. It's the load which we've normalized to be 1. So there's it's a step function. And now, is that true? Does that actually solve the differential equation? What's the differential equation for W? That's the equilibrium equation, and here's the right-hand side. And there's a minus. Did that get lost? Let's not lose that. Yeah. There's a minus dw dx. So do you see? Minus dw dx equals step function with the boundary condition w of 1 equals 0. So again, right? Minus dw dx. Yeah, let's write that in. Here's the differential equation. Minus dw dx is the step function at a. And why do we step down instead of up? Because of the minus sign. Right, because of the minus sign. So the solution is a step down, and of course it has to be adjusted to match the boundary condition. And because we wanted to end up with w of 1 to be 0, we had to end up here, and therefore we had to start from there. Really, I'm just working upwards. I'm doing it's like back substitution, working up the bar. Nothing's happening here. Nothing's happening. Nothing's happening. W is 0. There's no internal force, and then at that point something happens, and from there on the internal force is equal to that weight, which I'm taking to be 1. Okay, tell me u. Tell me u of x now. What's the displacement? X going here, expecting something to change at a, and ending at 1. Okay. What do you expect for displacement? Let's do just common sense first. Common sense. What's happening here? I'm giving a great big pull at that point, and not below. So let's take below first. What's happening below? U is a constant. Yeah, the whole thing is going to drop down rigidly. So I'm expecting u to be a constant here, but not 0. Just it's going to drop. And what about in here? It's going to, yeah, what's the displacement going to be? Yeah, it'd be linear, an ax, that's right. Because it starts at 0, but, it's the whole thing, the stretching is uniform, but the displacement, of course, then is linear. So, actually, we could draw it here. We're expecting to go up and then to stay constant, right? Now, just do I have anything else to? So that's my u of x. And like it has, both w and u are best written in 2 parts, before a and after a. I don't think we want to write one function that does this. But what are the pieces here? The pieces are u of x. Let's see, what's the differential equation there? And here u of x is a constant. So okay. What are these amounts? Let's to get it all straight. let's see, everybody knows that it had to start there. Why? Because the boundary condition said so. And then from that point, I just looked at the differential equation. What is the differential equation? Let's see, what's the differential equation for u if I know w, which I do. That's the beauty of this fixed free problem. I could find w straight off before finding u. So like I integrated once to find w, and then I integrate again to find u, because u is, so what's u? What's the equation for u? U is getting the derivative is e, but then c is 1. So u is just d, what is u? What's the equation? Yeah, the du dx is w, right? Du dx is e, but that's the same as w here because I took c to be 1. So one integration, and I've got one boundary value. So that's like perfect. I just integrate, in other words, I'm integrating this function. Gosh, I'm making a lot of work out of that. I've integrated this function and got that one. So u of x, this was 1 there because we made it a unit load. So u of x will just be x, it's integral. And what will u of x, what's the constant in this range? It's reached the height a, and it stays there. Right. Okay. That's the solution to the fixed free problem. Let's look at, so we took it in 2 steps, because this particular fixed free problem with one boundary condition on w allowed us to get to w right away, and then subsequently use the one boundary condition on u to get to u of x. But so if I put those together now, the complete differential equation is this one. And do you see that this satisfies that equation? Let's see, what are we going to call this type of a point here? That's a very important point. It's not a delta function, of course. It's not a jump. It's not a step. We need a name for what's going on at that point. A ramp might be a good word. We could use the word ramp, because that certainly reminds us of a ramp. Or a corner in the problem. And what's happening at a corner? What do I mean by the derivative is taking a jump, right? The derivative, the slope, is jumping, right? Jump in slope. Jump in slope, right? And that's is that what the differential equation would like us to have? Sure. The second derivative of this function, well, with the minus, is supposed to be a delta. So the first derivative is supposed to be a step. So the function itself is supposed to be a ramp. And the equation is saying, it's telling us something about what happens at that corner. It's saying, what is it saying is happening at that corner? There's a jump in the slope. And what's the amount of the jump? What does the slope jump by? It jumps down by 1. Well, let's call it a jump of -1. Because the slope here is 1, and here it's 0. So the slope dropped. And here, of course, here's our picture. There's the slope. It dropped from 1 to 0. So it's, and the reason was this minus sign. The minus sign made it a drop instead of a increase in the slope. Do you see that picture? And I believe that we could, I mean, if we kept those matrices that were there, the matrix with the 2 in one corner and a 1 in the other corner, and the A's, that A and A transpose that produce it, we could do the same in the discrete case. I would like to spend the remaining minutes, hours, solving the second problem. Okay. Which I guess may not be as easy. So what's up with the second problem? The physics is I'm now fixing the bottom as well. So physically, what are you expecting? It's fun to at least visualize what's happening. So we have this bar, like a column in a building, and then we hang a load at a point, and what will happen? Yeah, that's right. It'll stretch as before. There'll be stretching, uniform stretching above, and uniform compression below. I'm expecting. So are you expecting a W to look like? Now, we don't have this boundary condition W of 1 equals 0 anymore. In fact, we don't have any boundary condition on W. And I think, just based on common sense, we would expect that's a positive W, so that's a compression. And then, that's a tension. The bar is in tension here. Tension above, and that's W positive, and compression below, and that's W negative, and I think that's what the graph is going to look like. And constant in each piece, because there's no force acting, no external force acting within the piece. And the drop will be at A, and what will be the amount of the drop? Between the W, the positive W above the load and the negative W. What's this amount? It's the weight, which I've taken to be 1. Yeah, right? If I put in I hate to use another letter W, I should do better. But anyway, we've taken it to be 1. That drop will be 1. What is W? It's the integral of the delta function. It's the integral of the delta function with a minus sign, so it's a drop. And the delta function's been centered at A, so the drop occurs at A. But now what's up here? That's what it'll look like, but there's an arbitrary constant. There's a constant here. I haven't settled this. I've settled that this distance is a 1, but I don't know these numbers yet. And I can't find them out from the W equation because I haven't got any boundary condition on W. Previously, fixed. Now I'm doing fixed. So let me get the blackboard up to date. Now I'm doing fixed. I've got 2 boundary conditions on U and none on W. My matrix A is rectangular. I can't invert to find W. My operator is, morally speaking, rectangular. I can't. There's an unknown constant here. The thing has a null space. This A transpose has a null space. The null space is W. If I have a solution W, I can add a constant, and I've still got a solution. And that constant, I don't have any boundary condition to make it go away. So, in other words, the only way I can figure out the numbers here is to get on to U. So this is going to be some slope, what shall I call this? That'll be S, the original slope. And this will be S minus 1. Is that all right? But I don't know S yet. I don't know it until I come over here and figure out U. Okay, so tell me what U looks like, and then we've got this thing. Okay. So tell me what U is like. Starts at 0 and ends at 0. That's the one thing we definitely know. And it does something at A. And what will it do at A? It changes, its slope changes sign. Because, in fact, this is the picture of the slope. Right. And the slope drops by 1. So we've got it here. It goes up, so the slope is constant. So the slope is constant, slope S, so it's Sx, reaching some point Sa. And then it's dropping at what slope? What's the slope here? S minus 1. And so what's the function? Let's see. Somehow out of this is going to appear the number S. This has to magically... So I guess, let's see, how shall we do it? We started, for this linear function here, I don't know how you would like to, everybody for himself at this point. All I want to know is the slope here is 1 minus S. And I want to choose the number S just right. So that if it goes up with slope S to the point A, and then comes down with slope 1 minus S, I want it to hit 0. S minus 1 would be better. Okay. Should I leave that one? Or do you want to, any suggestion on what S is here? Let's see. We should be able to do this, right?
Two conditions.
Yes.
SA over A equals S.
Right. And I want to make those things match. Well, okay. At this point, I don't want the bar to break, we could say. At this point, U should be the same from both sides. Okay, so the same from both sides. All right. U on the left side, U minus is SA. And what is U coming from the right side? That's what we haven't really pinned down. Let's see. It starts at 0, and I'm looking for a straight line that goes through 0 at x equal 1 and has that slope. Okay. Let's see. How about S minus 1 times x minus 1? Would that do it? I said as everybody for himself here, so you may have a different, smarter way to look at it. But at least I found a function whose derivative is s minus 1, good. And at x equal 1, it's gone. Is that okay? So that's what that function is. So maybe I should have left the x here. U coming on the left is Sx. U coming on the right is s minus 1 times x minus 1. That has the right slope and the right boundary condition. And then at A, they're supposed to meet. So that finally does it. At A, this SA from the left is supposed to agree with S minus 1, A minus 1 from the right. That's the magic equation then that has to determine S. And it's easier than it looks because an SA is going to be on both sides and cancel out. So I'll get an expression for S, for the slope. Let me, because I want to keep that idea foremost rather than the algebra. See, that's what happens in calculus courses. Algebra like takes over. You become just like a demon factorization problem. But that's not what mathematics is about. It's about what's going on here. And what's going on is a continuity condition. We expected the slope to jump, the function to have a corner. That's a corner. You'd have to call it a ramp too. And the slope changed by 1. And the boundary conditions sort of sent them both up from the sides. And the continuity condition that U is a continuous function You see, if the displacement wasn't continuous, the bar would break apart there if we had two different values of u. It's the same value of u, positive value, it drops, all right? So u, the displacement is positive. Everything in this bar goes down. But it goes down most at A. It goes down most at A. Okay, so that leads to the equation for S. So you see that, as expected, the fixed problem was a little tougher. The fixed free, we could find W, and then just one more integral gave us U. The fixed, we found W, but with an unknown constant, and then we couldn't resolve that constant until we got to U. Okay, so quick recap then. We're speaking about our familiar framework, but now derivatives have entered, and somehow we still have to discuss more this idea of the transpose being minus the derivative. So more to say about that. What does transpose mean for derivatives anyway? Then we got the delta function into the problem as a point source and solved the two principal examples. And just to finally end with, what have we found? When the right-hand side is a delta function, the solution is called the Green's function for the problem. So we have found the Green's function for this fixed boundary condition. This u of x is the Green's function, named after this guy who did a lot of the central formulas for calculus in one and several variables. Okay, so that really is then the simple differential equation. The boundary conditions you saw produced all the interest, and now we've got the solution. Okay, so that's lecture 7. Lecture 8, we'll see partial differential equations coming. So we're really moving along. Okay, so I'll